Well, some examples in the book. Dwayne Gish, his story of his life. He went to University of California, Berkeley. And most people, I didn't really know much about his background until he did a chapter for the book. He was, for many years, was one of the most well-known creation scientists. He's retired now, but he did his work in biochemistry at Berkeley, University of California, Berkeley. He also was a researcher for Cornell and industry for a number of years. Henry Morris, also well-known, and many of us, I didn't know much about his background, and he PhD at the University of Minnesota. He also was a chair and professor of hydraulic engineering at Virginia Polytech Institute and State University, often called just Virginia Tech. And I go into detail, or he goes into detail, in his life, in why he accepted creation. He was at one time a theistic evolutionist. He was not a creationist, a young earth creationist. Another case is Raymond Damadian, who has a medical degree and was a professor of biophysics at the State University of New York. And he's well known for inventing the MRI.
Wow. And
there's been quite a bit written about him and how he developed the MRI. One thing he told me was that when I was developing the MRI, people said, "You're crazy. You can't put people in magnets. It's not going to work. You can't do it." Then when he developed the MRI, and it finally was proven to work, and of course now it's a standard technology in many hospitals, then his friend said, "You didn't do it." So when he was trying to do it, they said you couldn't do it. When he did do it, they said you didn't do it, which is, even though he has a legal patent, he had to go to court to protect his patent. He did prevail in court, and he is the legal inventor of MRI.
For the record, he did it.
He did it, yes, he did it.
All right.
Although others improved upon it.
Sure.
But that's common with most inventions.
Oh, yes.
And, but he did the initial work which showed that MRI technology is possible. You can image bodies using magnetic resonance imaging.
And he was a creationist.
And he was an outspoken creationist.
Great.
He was very successful. It's said that when he began doing work, he did mostly surgery on infants.
Yes.
When he began doing work, the success rate was like 10% for many surgeries. After he perfected the techniques, the success rate became the reverse. 90% success, 10% failure. Adler's one who I always respected. He was the editor of the Encyclopedia Britannica. He was a professor at the University of Chicago. And he also, which is one of his greatest accomplishments, he developed this series called the Great Books Program, which a lot of people have heard of. And there's the Great Books. He took all the historical writings and selected from those 54 volumes of material of what he considered the greatest people in our history, Aristotle and Plato and various other people. And this set, as far as I know, still in print. Most every large library has it.
Sure.
I have a set. I've had a set for many, many years. It's, in fact, there was a Great Books program where people would get together in groups and study the Great Books work, which he assembled. And C.S. Lewis, it's not too well known that he was a very active creationist opposed to evolution, although he didn't write a lot about it directly. You kind of have to read between the lines to understand what he had to say. He wrote a lot against naturalism, which of course is a central tenet of Darwinism. And later on in his life, he did write a book called The Great Myth. And in that small book, actually, in that he really effectively dissected why evolution could not be true. But ironically, that wasn't published until after he died. He was kind of fearful of being too open about his opposition to Darwinism because he felt that it would detract from his main message, which was a Christian apologetist.
Right.
But he clearly did have major reservations for
that. In fact, it was an entirely different worldview. Truly one of the great minds of the 20th century, C.S. Lewis.
Clearly, and there's Cover magazine story about him, C.S. Lewis, on Christian History magazine. And he's probably most famous for his work, which has been translated into movies and many languages.
Dr. Bergman, as you were talking and writing with the men and women whose stories are told in this book, do you ever come to a point where you think the truth is going to become so overwhelming that the lies simply won't hold water anymore?
It seems that way if you're willing to look at the reality, if you're willing to study and read what people have said and what we found through science about reality.
and the truth will prevail.
Irreducible complexity is the idea that in order for something to function, it must have a certain minimum number of parts. A good example would be a human being. For a human being to function, it must have, absolutely must have, at least part of the brain. It must have a heart to circulate blood. It must have a certain level of blood. Must have certain organs so it can obtain nutrition, etc. So therefore, you can only reduce a human being so far before it no longer is alive. And that, of course, causes death. And we find when we look at the world that just about everything is irreducibly complex. And I should mention, this does not mean that one cannot remove a part. It's often assumed that irreducible complexity means you cannot remove a certain part. It says there's a certain minimum number of parts that is necessary in order for something to function. I conclude that everything is irreducibly complex except what they call the fundamental particles. One set is called quarks. And you may not be aware of that, but there are 6 basic kinds of quarks. There's top, bottom, strange, charmed, and up and down. Those are the 6 kinds of quarks. So they are fundamental particles. As far as we know, quarks cannot be reduced farther. That's it. And the next one is leptons. And leptons we're probably more familiar with. There's electrons, neutrinos, at least electrons we're familiar with, tau neutrinos and muon neutrinos and so on. By the way, quarks are assembled to produce things like protons and neutrons. Protons are 2 up quarks and a down quark produces a proton. And 2 down quarks and an up quark produces a neutron. And then there are bosons. An example of bosons would be photons and gravitons. Everything in the universe is made out of these fundamental particles. And a common example is a mousetrap. It's a very simple example because you can notice if you take away the base, it won't function. It won't work. You must have the base. Now people say, well, wait a minute. What if you take the base away and attach these particles, these parts here, the sections, to the floor?
Well, the floor just becomes the base.
Right. And I point that out to students because in chemistry this is a central concept, and they notice right away, well, you still have a base, it's just the floor becomes the base. So a mousetrap is irreducibly complex for it to function, and we're talking about a mousetrap like this, which functions in a house to catch mice. People say, well, you can dig a hole and catch mice. That's true, but it's not very convenient to do in a house. And periodic table, all of the elements are irreducibly complex. You must have a certain number of protons, electrons, and neutrons to produce all of the elements. And a good example is carbon-12. To get carbon-12, you must have 6 protons, 6 neutrons, and 6 electrons. You cannot get carbon-12 any other way than have 6 protons, electrons, and neutrons. If you have a different number of electrons, guess what? We have an ion of carbon. We don't have a carbon atom. We have a carbon ion. If you have a different number of protons, you of course have another element. If you have a different number of neutrons, you have carbon-14 or carbon-9 or carbon-12. Okay, examples. Well, obviously, radios. To have a radio that functions, you must have a certain minimum number of parts. Television is a good example. When the television was invented, in order to get a television system that worked, you had to have a unit which would pick up the light, which would translate the light into electrical impulses, which would send the electrical impulses through the air eventually, and then you had a receiver which picked them up, which translated them back into light, so you could see the television picture. And that's a good example. MRI and so on, another example. Looking at this whole issue is the idea of intelligent design. All that says is that we can look for evidence of intelligence in nature. And the best example, the most common example, is the watch. The watch obviously was intelligently designed because, well, we can see the intricacy, the interconnectedness, and it's also irreducibly complex because if we remove a couple of these gears, it's not going to work. It's not going to function. And this is a good example. We're going now into a bacterium, and now we're going into the wall. This is the wall of the bacteria here. And now you can see parts are being built around it. And these parts have to be manufactured somewhere else. They have to be shipped to the work site. They have to be assembled in the right place at the right time. And they have to be put together so they stay together. You can't just lay them down.
Slow down and tell me again. That was a bacteria, and in its wall, what's being built?
This is a bacteria flagellum which is being built.
Okay.
And you'll notice there's lots of parts here.
Yes.
All of which have to be available, produced at the right time, at the right place, shipped to the right place, and eventually, of course, we end up with this bacterial flagellum. This right here is a jig to make sure these parts are assembled properly. And then this jig is left, it's moved out. Another jig is put in its place. And you'll see the other jig come in here in a second. Here we go. And this jig then allows the last part of it to be assembled properly. There we go. And eventually, it becomes longer, and we have the bacterial flagellum. And there we can see this is the bacterial body itself. In this case, we have, it looks like four flagellum, which allows the bacteria to move around, kind of like a tail. And here we can see how the flagellum itself is built up. Now, it looks pretty simple, but
it's pretty complex.
It is pretty complex. And these are the parts. You can see this is D0, D1, D2, D3. These all have to be manufactured at the right place, assembled at the right time, and once they're assembled, then it, of course, functions as a movable, flexible tail, which you can see here in a second again. I've often wanted students to make a model of this. You could assemble it without glue, and this whole thing would function. And here you can see in more detail the jig. And we can see then the bacterial flagellum. All the parts are named, so we know what they are. And these have all been studied individually. And we can then look at how it is assembled and how it functions.
That's amazing. The complexity of that is absolutely amazing.
They call it a protein motor. And here you can see more details, the same thing. And this right here, this bacteria, this is E. coli, and this has a single bacterial flagellum. And there you can see more details. When one looks at this, it looks like it was designed and built. Looks like it was manufactured.
Engineered and then designed and built.
Engineered, right.
Yeah.
And this has caused a lot of people to just be amazed at the design and the intricacy of even in bacteria. And this is an actual photograph, a transmission electron microscopy photograph of the bacterial flagellum. So we can see indeed that these drawings, the previous were drawings, the drawings are fairly accurate in showing actually the detail that exists in the bacterial flagellum.
It really does. That's amazing.